Hello, I'm Geeta S. Nazare, working as a technical director for ARM Tools. Today I'm here to discuss the interesting topic on significance of debugging in embedded systems. So what does the word debug means? So debug is basically removing the bugs from the system. So usually embedded systems work in a resource-constrained, real-time and safety-critical environments. Even a single bug will make the system with safety hazard or with overall system failure. So how will the embedded system alert to the programmer or a designer there is a bug or issue in the system? Thanks to the exception. So with the help of exception, the embedded systems alert to the user that there is some runtime issue or unusual fault is being observed. With the help of exception, the user can easily bring the system back to the normal condition, or he can safely shut down the system, thereby maintaining the overall stability and potential of the system. So in today's video, we'll be discussing about the exceptions. So before jumping into this exceptions, I would like to first emphasize the architecture or the processor core which I've selected for today's video. So today I have selected Cortex-M3 core because that processor is being used widely in the embedded systems, and it was the first ARM processor core released by the ARM to the market. Basically, Cortex-M3 is specifically used in industrial, automotive, IoT applications, and it has a very well built-in fault handling mechanisms which will make this Cortex-M3 processor viable and easily usable by the engineers. So Cortex-M3 comes with various faults and exceptions. So it is capable of handling various faults and exceptions. My today's emphasis is on hard fault handling. The reason being, I'm pretty sure many of the engineers or designers would have come across this issue where the processor has ended up in hard fault handler. So handling of this hard fault exception is a very key importance to know for the user or a developer. By writing the exception handler, we can easily get the processor back to control, or we can easily find out the reason for the exception, because exceptions are the way to find out the root cause of the issues in your embedded systems. So before jumping into how the exceptions are handled in Cortex-M3, I would like to first emphasize and precisely help you note in what scenarios Cortex-M3 generates the hard fault exception. So first scenario is when the processor executes the code from some invalid memory. Basically, if it's system control space which has a memory attribute of execute never, in such cases the processor generates fault exception. Second is if the processor tries to access from data memory from some restricted memory region. Third, if the processor encounters some undefined instruction, or when the processor encounters divide by zero. So now let's quickly jump into the PowerPoint slides where I have just prepared to show how the exceptions are handled, and then we'll quickly jump on to the demonstration of debugging in embedded systems. So now let's see how the exceptions are handled in Cortex-M3. So I've just prepared few slides to show how Cortex-M3 interrupt handling mechanism is quite different from other processor architectures. So coming to the traditional architectures, even in the legacy versions of ARM cores, how the interrupts or exceptions are handled there. Whenever the exception or interrupt occurs, the user has to explicitly push all the registers onto the stack and pop all the registers back from the stack at the time of exception entry and exception exit. Or compiler has to push in all these instructions at the time of generating of the code. But thanks to Cortex-M3 architecture, this particular feature is micro-coded in the architecture itself. It is hardwired kind. So as soon as exception or interrupt occurs, the registers are pushed onto the stack and the exception vectors are automatically fetched from the interrupt vector table. So how this mechanism is handled? It has been handled by nested vector interrupt controller, precisely NVIC. So now let's talk about how this particular micro-coded feature improves the interrupt latency in Cortex-M3. If you take a traditional architecture, as I said, pushing of the registers onto the stack and popping up back occupies more processor cycles, and the interrupt latency can vary from anywhere from 46 cycles to 50 cycles. But in case of Cortex-M, because of this micro-coded mechanism, processor can quickly jump to the exception handler in just 12 cycles. So you may ask me, what is the scenario if it is nested interrupts? True. Whenever there is a nested interrupt, based on the priority of the interrupt, the processor can quickly jump to the Pending interrupt in just 6 cycles. It's true, exactly. What you heard is right. In just 6 cycles, the processor can switch from the existing interrupt to a high priority interrupt. And this concept is called as tail chaining. Now coming to exception types. So you might have heard of exceptions or interrupts. Sometimes users tend to use it interchangeably, but they are totally different when it comes to ARM architecture. In the ARM processor core, you have both internal exceptions and you have external exceptions. So what are those internal exceptions? We have SPC, supervisor call, pend supervisor, false and sysdig timer. External exceptions are your reset, interrupts and faults. So what are those interrupts? So what are the components which come outside the ARM processor cores are nothing but your peripherals. Peripherals like watchdog timer, I2C, SPI, USB, ADC, the peripherals which are capable of generating the interrupts, those are all come outside the ARM processor core. So hence, in ARM technology, we keep these two words differently, exceptions and interrupts. You can also see the words here faults. So faults can also be generated by the peripherals or from other part of our application code. So in this specific slide, you can also see application code and exception code. So application code is your main software code and the exception code is nothing but your exception or an interrupt handler. So Cortex-M3 operates in two different modes. We have thread mode, we have handler mode. So usually our application or software application code executes in thread mode, whereas exception usually executes in handler. So now we see processor mode usage. So when you give power on reset to a processor core, Cortex-M3 processor core, the processor enters reset. Reset itself is a high priority exception in Cortex-M3 core. So the processor first executes reset handler. Reset handler is the only exception which the processor executes in thread mode. Other than that, other exceptions, Cortex-M3 processor executes in handler mode only. So in application code, when you're giving the reset, the processor application code will come to the exception code from the thread mode to handler mode, and then it will service the interrupts. So one thing to take away from this slide is reset handler or reset exception is the only fault which the processor executes in thread mode. All other exceptions has to be executed in handler mode using main stack. So coming to vector table for ARM v7m architecture, because Cortex-M3 is part of ARM v7m architecture. So ARM interrupt vector table for Cortex-M3, ARM has given 496 external interrupts and each interrupt has an exception. So this interrupt table is very interesting because with the help of this interrupt table and by the entry of these two locations, that is 0th address and the next address which is 04 address, the processor will get to know from where it has to start the code execution when the reset is being asserted on the processor. So now let's come to reset behavior. So here you can see at the 0th address, when we are giving reset, the reset input is asserted. So the 0th address will have the initial value for the main stack point. Reset handler is always executed by the processor core in the thread mode using the main stack point. So that value is loaded to the main stack pointer, which is R13. So alternate functionality of register R13 is nothing but the stack pointer. And then the processor will get the address, which is basically precisely PC program counter from where the processor has to start. So the next entry in the vector table will have the address of the reset handler. So from there the processor goes to the reset handler and it executes the reset handler in thread mode. This is important to note. And then reset handler can jump to your main function, the main function which is written by the user. Now coming to exceptions. So exceptions can occur even in a software application code, even before the processor hits the main function or after the software application execution has started from the main function. Irrespective of the scenario, whenever the exception occurs, the current instruction which the processor is executing will be stopped, means the pipeline will be flushed. Cortex-M3 has 3-stage pipeline. In that, this pipeline will be flushed and processor will go and fetch the address of the exception from the vector table and it jumps to the exception handler, and this exception handler is executed in the handler mode. After this, the exception handler will return back to the main application. Now coming to interrupt stacking. So when the interrupts or exceptions are generated, I said in Cortex-M there is a microcoded feature implemented. So all the registers are pushed onto the stack. How is it? In case of Cortex-M3, it has a Harvard architecture, means it has two different buses for instruction and data bus. So through the I-code bus, the processor goes and fetches the address from the interrupt vector table. And through the system bus, all the registers are pushed onto the stack. In case of other architectures, where the interrupt latency can still improve or still increase when there is a architecture has a one human architecture, like ARM7 or ARM9 processor architecture. There it is one human architecture, and here the processor has to wait until the bus is freed, because it has to use the same bus for pushing on the registers onto the stack, and same bus it has to use to fetch in the address of the exception handler from the interrupt vector table. So what are those registers which are pushed onto the stack? Stack is a decrementing stack in Cortex-M3. As soon as exception is generated, all these registers are pushed onto the stack. R0, R1, R2, R3, R12, link register, return address, and PSR. Return address is nothing but your program counter. Link register always will hold the address of the next instruction from where the exception or interrupt was generated. PSR is optionally loaded to ensure that stack is 8-byte aligned. If the stack is not 8-byte aligned, then you may encounter the misuse of the stack memory, or your stack memory will be like you need to use the padding of the bytes to ensure that the stack is word aligned. And sometimes for processors also, if the stack is not word aligned, it will also generate an exception. Now coming to exception return. So what is this? Link register I was telling, which holds the address of the next instruction so that the processor can automatically resume the normal flow of the execution as soon as the exception or interrupt has been serviced. So what does this execution return indicates? The link register also has one more, it plays additional role of this execution return value. This I'll demonstrate when I'm doing the demonstration of this exception in my program. So at the time of entry to the exception, execution exe return holds a value, and at the time of exit, it holds another value. So at the time of entering to the exception, the exe return, which is a 32-bit register, many of the bits are reserved here. The mainly less be 5 bits are more significant for us here. Why? The bit 2 will decide the registers are pushed onto the main stack or the process stack pointer. So let me talk about process stack pointer, because I have not talked about process stack pointer till now. So Cortex-M3 supports two different modes, as I said, handler mode and thread mode, and it also has two stack pointers: main stack pointer, process stack pointer. So when will we use this process stack pointer? Whenever we are using an RTOS based application where kernel or a scheduler executes with main stack pointer and your threads or tasks executed process stack pointer. But in my application, I'm writing a bare metal application where there is no OS involved. So I'll be using the main stack pointer. But always the users tend to write the wrapper function, assembly wrapper, to find out which specific task, which specific stack the registers are pushed onto. So how they will know? By reading this second bit of this link register, they can easily make out which particular stack the registers are pushed on. So in my case, it will be main stack pointer. So for me, it will be easy for me to see the registers, which I'll be demonstrating soon. So these are all the values of exe return. So you have various values. So in my program, you'll be seeing this F9. So it is returned to thread mode using main stack and restore basic stack frame. The basic functionality of this exe return feature is to make the processor understand. As soon as at the time of returning from the exception, link register holds this value. To tell the processor, is there any pending interrupt waiting for the processor, or is there any, or there is no pending and the processor can directly go back to the main function. So that specific information is stored in this exe return. So this is how nested interrupts are also very well managed in Cortex-M3 in comparison to other architectures. So coming to fault status registers, basically these are the two registers when processor encounters the exceptions, and with the help of this fault state registers, without getting panic, we can easily read these registers and understand what was the issue for the fault. And I'll be talking about hot fault handler because it's a master fault handler in the Cortex-M3. And any faults generated inside the processor core or due to the application, the processor will come to hard fault. Now let's go to the demo part of this exceptions. So I've been talking about how this exceptions can be handled. To continue with this demo part, I have used MDK software, which is a industry standard software and widely used by many engineers and programmers. So I'll be demonstrating this exception feature with MDK. So I have written a simple program here, basically for fault handling. So this specific project will show you in what all scenarios the hard fault exceptions can be generated. So my program starts from the main function, and here I'm enabling all the faults. Basically, as I said, Cortex-M is capable of handling many faults. There is usage fault, there is bus fault, there is memory management fault, and there is a hard fault. So if any of these faults are not enabled, usage fault, bus fault, or memory management fault, processor will still come and stop at the hard fault exception. So in this part of the code, I'm just enabling the exceptions for usage fault and bus fault, because in my program, I'm trying to demonstrate even the various faults also. But my main focus will be on hard fault handler. Okay, then I'll be injecting the fault. I'll be injecting the bug. So I want to explicitly inject the bug. So what bug is what that I'm introducing? I am making the processor to write it to a invalid address. Precisely, it will be writing to system control space. So trigger invalid jump. This is a function. So this function is trying to execute the code from this address. And this address is part of system control space. Upper 512 MB of this 4 GB memory space or memory map of the Cortex-M3 is a system control space. And that has attribute as write, read only, and no execute never, XN. So here I am explicitly making the processor to execute the code from that specific address, so that it can generate an hard fault exception. So all other invalid write, divide by 0, all this I've just commented, so that I'll be demonstrating only on this part. So when the hard fault handler is generated, the processor comes here. So now I'll just quickly tell you what are all the basic mistakes the programmers or the engineers do here. Suppose this is the function exception handler name. I have given hard fault handler. So now I'll build this project. This builds project without any errors. Okay, now let me enter the simulation. I'm not connected any debugger because I want to make the viewers understand that such exceptions or interrupts can still be serviced and handled in simulator as well without connecting target board. So still they can simulate the exception and interrupts and thereby get the processor back to normal state. Well, now let's put the breakpoint to the hard fault handler, and you see the processor is stopped at the hard fault handler. Okay, so you may ask me why it is not going to my exception handler though I have defined it. The reason being the function name is not matching. This is a startup code. Actually, as I said, processor has to execute the reset handler. The reset handler definition is part of this startup code. And this has the dummy interrupt handler and exception handlers for all the interrupts and exceptions the processor generates. So here I am using LPC1768, which is Cortex-M3 based MCU from NXP. So now, though it comes here, when I try to run, nothing happens. Why? I have written exception handler. That's because the function name doesn't match. And it is case sensitive. It is not that. So now what I'll do, I'll go to hard fault handler and let me come out of debug session. And now I'll change this to capital H. If you want to know, either you can modify here as per the startup code, or whatever the function name you have given, same thing you have to modify it here. Either the way you can do. So now let's see. Now after changing this function name, ISR handler name, the processor will now enter the exception. So that I'll demonstrate with the help of breakpoint. So now we can see the processor has entered the hard fault handler. The breakpoint here I've used to just to show you that the processor is entering the hard fault exception. So once the user has to be very careful here on when you're giving the name for the exception handler. So as I said, you can either modify here or change it in the startup code, but see that both places it matches so that processor can understand, because processor fetches the address of the handler from the interpreter table. So dummy interpreter table is already been given in the startup code by NXP team. So we have to modify there. So be careful on that part. Now, as soon as the processor enters the hard fault handler, so now we can see many things with the help of the powerful debugging features of Keil MDK. One can easily make out what was the reason for the exception. So now let me demonstrate that part to you. So as soon as this hard fault handler comes, you can see in call stack and locals, there is a hard fault handler and main. So here if you select hard fault handler, right click and show caller code. Here in disassembly address, it shows the instruction, the next address of the instruction which caused this exception. In our case, it is 0, ending with 7Fs and 0. Next, here you can see fault reports. These fault reports can be accessed from peripherals, core peripherals, and fault reports. So fault reports basically tell you in total what are all the faults or exceptions the application has generated. So in this video, since I'm explicitly making the processor execute the code from the illegal memory, so here you can see hard fault status register is showing forced. Forced in the sense this specific exception is being not a fault, actual fault generated by the application code, but by the software code which is trying to execute the code from the invalid address. So precisely this specific exception comes under memory management fault. So in my program, I have not enabled memory management fault. Hence, the processor comes to the hard fault handler. This hard fault status register first indicates this particular exception has been escalated to hard fault handler. Now we want to know what was the reason for the exception, what was the reason for the issue. You can see here in the under the memory management fault, there is IACC violation. Instruction access violation. It's clearly indicated that due to the execution of the code from the invalid memory region, this particular exception has been generated. Right? Then you don't have any other faults here, bus faults, usage faults. So all the faults is just shown without any values. This fault related to memory management fault. So this specific block, it shows this specific value. So now coming to registers, some important things to show you in the registers. So here you can see banked. In the bank, you can see I'm using MSP. As I said during my presentation that this is my bare metal application without any RTOS. So I'll be writing my code completely with MSP. So now you can see main stack pointer addresses 1 followed by 5 zeros and 200. Now quickly go to memory window and type in the address of that stack memory. As soon as I enter the address of that stack, you can see all the registers stacked here. So you can see this is your R0 register. You can compare that here 27 and you can see R0 is 27 here. Next is R1 is A and R1 is A. Then R2 is 1. Then R3 is E followed by 6 zeros. Next comes R12. So R12 is 0, 0. So this is your PC, program counter. And this is your link register. And this is your PSR register. So link register, as I said you, this is storing the value of exception return, exc underscore return, the one which I showed you in the slide. Next thing here to show you is XPSR. So you can see here ISR 3. So from the vector table, from the slide I showed you, hard fault handler has the inter vector number 3. See, that's what you are seeing it here. Right? And so further, when it enters here, it shows invalid function pointer jump. So this printf statement I've given from the main function. So without connecting even the hardware, I'm able to see my printf functions. Okay. So when I run this program, it shows me, this is my CFSR value. CFSR is configuration fault status register. Basically, CFSR is a combination of all these faults. So some bits refer to usage faults, some bits for bus faults. The lower 7 bits, lower 8 bits is for memory management fault. In that first bit is for ICC. So same value you can see CFSR 1 and HFSR is 4 followed by 7 zeros. Here it is HFSR is again a 32-bit register. In this 30th bit is been set. So 30th bit indicates, you can see here, it is a forced value, right? So now in this particular video, I have just shown you how the faults can be generated. In fact, I have injected the fault. I have explicitly generated the hard fault exception, and I'm just printing the registers to show these are the fault registers the programmer or a designer has to look at and thereby get the processor back to normal control. So now with this address, as I said you, at the time of exception entry, that specific address you can make out, okay, program, because of this processor executing this instruction, the specific exception has been handled. So you can correct it back, come out of the simulator, correct it back, rebuild your project, and your processor is back to the normal flow. So all the printf messages, you can see it in the printf view. So similarly, this project I have written for even divide by zeros, usage fault, everything, but I wanted to show the memory management fault, and it is being handled by the hard fault. So I have used this specific program for showing you the exceptions. So these are some of the features of the microvision debugger which you can easily use and understand where the fault has been generated, what was the reason for the fault, which specific address it was generated, and you can also see the stack contents, all the registers and everything. So to conclude on this, I would encourage the designers and the programmers, so please use the exceptions features given by the Cortex-M architecture or any architecture and make your system bug-free and develop a more reliable and stable embedded systems. And if you are using Cortex-M3, you can use this beautiful built-in inter-mechanism, built-in Cortex-M3 feature, and use this industry standard Keil MDK software to develop your code and debug your code. Thank you. See you soon.